okay, the issue that we're tackling is bounding box with Joe. We'll find out who Joe is with all the dead fish that we've encountered so far. The problem statement is we are trying to classify numerous amounts of dead fish into 7 different classifications plus no fish. The approach that we took in is identifying, so the first step that we took is identifying possible use cases or possible encounters to tackle this issue, right? So the first that we took is skewed data, and this is what we can see. Now the issue with with this skewed data is that we do not know what our test set is like. It can identify albacore tuna really well, but the rest of them not so much. Now there were a lot of cases in our, there could be a lot of possible cases where there's no fish, right? And as you can see in this image, there is no fish. But our bounding box still recognizes some part, which is this. It recognizes this as no fish. Why do you think that's possible? That's because the bounding box did not find any fish, but it found the best possible box that signifies no fish.
Well, in other words, when we saw data, we also noticed that like one of the standard approaches to this problem is to identify all the fish all at once and then draw bounding boxes around them and say, okay, this is this kind of fish and whatnot. But as we noticed that like when you do that approach, then you actually end up with a lot of no fish data as well. So as soon as we saw those little JSON boxes for no fish, we thought, what is it displaying? And it turns out nothing. So that's just background noise. So we have to deal with that then.
Our next issue was wrong sizes. Now, if you see all the images, we tabulated all the image sizes, and most of them did not turn out to be the same. And that's going to be an issue because we're going to have to resize everything, but make sure they still hold a good amount of clarity and definition.
Well, actually, as we all know, like many of you must have been thinking that why not just use a fully convolutional network, right? Because then we don't care about image size. But really what we were looking for here also shows up a while later, is that these images are of different situations, right? And that's typical. So if you go into a little bit of the background of the problem, that is you have a conservation agency, they want to see how many types of endangered fish are being killed, you want to somehow prevent that. And so you have a lot of diverse data. You have tourists, you have like, but you'll notice like there's a majority here, and we'll get to that in the later slides. So yeah, the distribution.
Okay, the histogram to show the same distribution, right? So the next case that we had was edges. Now, as you can see, fish is almost cut out over here. Over here, the fish is hardly shown in the top part, but it still recognizes this as fishes in the training image. Now, we also have the case of where our bounding box, which we took as a sample, cuts out the head of the fish, but it still recognizes that as fish. And now, there is a so this might be a good thing or a bad thing. Why is this a good thing? Because in our training images as well, there are a lot of fishes whose heads are already cut off. So this still recognizes this as a fish, and this still serves as a good example. But this bounding box itself is not recognizing the whole fish, and that could be a potential issue.
Especially, okay, maybe for fish, no fish, this is a great thing, but when we want to come down to the nitty-gritty of classifying what kind of fish it is, not having the head seems like a rather major issue. So.
And finally, we have backgrounds. Now, the first thing that we realized, okay, when you are dealing with data, you would want to go in depth to the raw data and actually see what's happening in the background, actually see what's happening in the images. And we realized that in that top corner, if you still can't see it, there, the watermarks. So the watermarks were a major role in almost 75 to 80% of the images. Now, if they were close to 100, that would be fine because the watermark is similar throughout all these images, right? So it wouldn't be that much of an issue. But if we have about 50 to 70%, that becomes an issue only because the system recognizes that watermark and expects that watermark also in a lot of test sets or while training itself.
It also showed us that, like, apart from the data classes which are given to us, that the aspect ratio and the size, which we normally neglect if we were just feeding it through a network, it also plays a role because it turns out all these images are sat-link images. That is, the 1280 by 720 images are all from sat-link. And that has a lot of connotations later. That's a new class which we can now exploit.
And then we have this relation. Now, if you look carefully, in all these resolutions, only 1280 by 720 do have watermarks. And again, like I said, that is an issue because most of it, while classifying your images or while the machine is classifying them, they have a watermark only in the 1280 by 720, and it would take that into special consideration versus the rest of them. Again, we have different backgrounds that we need to take into account. Why? Because the test set might not be what we expect, right? We need to diversify all our backgrounds and make sure that we can recognize fishes in almost any criteria.
So one of the more effective models, as I'm sure many of you would realize, is that since the area which we're detecting is so small in comparison to the rest of the image, if there's a finite number of backgrounds, then we could just use that, But again, this is satellite data, so we should think, okay, maybe these are going to be mounted in other areas, other fishes, other ships, all sorts of changes might be occurring. So we want to reduce the effect of the background.
Okay, so that comes to our approach, and this is how we actually thought about it. So we have really cool data, and we cut it into 4 pieces, right? So we have the data, we want to cut into 4 pieces to analyze where the fish would be and to process it further.
Okay, so basically this cutting it into 4 parts is essentially data augmentation, right? Because in the first step, it turns out, luckily, here we have bounding boxes already. So we already know, given an image, a total image, if we divide it into 4 quadrants, we already have the bounding box, so we know which quadrant it's going to be in. And the rest of those just became examples of no fish, which is great for us, because we want to train it on maximal no fish, but still somehow reduce the background problem. So we need more data, so that's how we get it. We could have also taken external data, but NDAs and stuff, so.
And then we tried to classify fish or no fish because we wanted to reduce the number of no fish. We wanted to keep the no fish out of the criteria. And so no fish is out. And out of the fish that we get, we take the best of the 4 boxes, like the box that contains the fish. And we create a bounding box. We make an even smaller version of that box to help the algorithm classify it a lot better. And then we move it into classes. So this is an example of fish, not fish, that we had in our data set. Oh, guys, by the way, I'm going by Pavlos' method. Take this in, because you saw a lot of dead fish already. Feel free to, take a few seconds over this. All right? So, like we said, we had to remove the watermarks, we had to crop it, we had to resize it, and this was the image before we wanted to push it into a bounding box. Right? As you can see, no watermark, in-painted.
No. We just did a simple crop because it turns out it's actually very easy using OpenCV, so yeah. And this is the labels which we got. And as you can see here, a lot of this is not really meant for us, but I'm assuming it came through like one of those tools which OpenCV uses to draw the bounding boxes, which is why it needs like things like class rect and other things. We won't be using that in our method. Okay, actually, what we did do, given the constraints of time and the fact that implementing a further bounding box is basically going to be an application of YOLO. I think we have a few slides on that, but what we ended up doing is a much simpler idea, and it goes back to what another part of our lectures talked about, right? What is an image, especially an RGB image, right? It's one image with 3 different channels. And if you plot a histogram of that, then you get a sort of unique-ish pattern. Now I say unique-ish because obviously there can be overlap. And the point is, if you have a lot of overlap, then you say, okay, maybe this is just like the other image, right? So if I take a picture of you over 20 days, then you'll probably have the same color distribution, adjusting for your clothes, right? So that's what we did, and then we simply did a k nearest neighbors there. Okay, so this is excessively simple stuff, but it does rather well. We'll see that later. So, okay, what about the classification? I'm not going to talk too much about that. You can start.
Okay, so as it says, YOLO means you only look once. What we're trying to do is we're trying to implement this ideal classifier. It has 75 convolutional layers that actually help you jump deep down into classifying what is, what not, and the several types of classification.
So a little bit about this. It basically, it predicts a bunch of boxes, then pools the boxes together, and it tries to find the ground truth. Okay, and to do that, it does some resampling, some rescaling. But yeah, okay, those are all the implementations. It actually works surprisingly well and very quickly. So speed is of the essence, right? So currently there's YOLO version 3, which is one of the fastest methods. So.
And finally, our model starts, bang. We have a 92% accuracy in 14 seconds. And this is just our baseline model. In 14 seconds,
Well, okay. Again, this is not. It's almost. No, this is just using the color histogram, the KNN. Yeah, it is actually. It is surprising. In fact, a more fun thing about this is when we remove the watermarks, we actually dropped a little bit in accuracy and our loss percentage gained. I mean, it got worse, and that's sort of to be expected because a lot of those are albacore tuna, right? So a lot of the data set is albacore tuna. A lot of the watermark data set is albacore tuna. You can get the idea, right? So a lot of the image, a lot of the coloration is coming from the tuna, which is why we had a slight loss. But it's still important to remove the watermark because later on, when we feed it through the networks, we don't want it to learn that watermark.
and that's all. Thank you very much.
We haven't finished it yet, but so it turns out this is actually done by the guy who came third. He did use an ensemble average as well, a different model. But yeah, he also did a fish, no fish, and then yeah.
Anybody who's coming up next?
Yeah, who's coming up next or questions? Oh yeah, sure.
The code?
Anybody else on this particular model?
This one or the one where we show the layout? Okay. Okay, so we're loading the image, okay, and then what we're doing is that using this CV2, right? And then we're extracting, yeah. Do you have it on Gitter here? Oh no, you won't have it here. Okay, damn. Just delete the rest and zoom in on that.
Which one? Left, right?
The right one, I believe. Okay, so the one on the left is actually just, we made a data frame of all the stuff. It's actually just a bunch of for loops, but it's my first time with Python like that, so. Here what we're doing, it's pretty basic actually. It turns out, yeah. So this is basically easily done. So all you're doing is that you're extracting a color histogram. That's it. It's Python. It does it for you. Well, so the basic logic is any image can be decomposed into like a histogram of like the RGB values, right? The intensity of R, G, and B, the different ones. And then we're histogramming them to get a unique distribution weight. That's clearer here. So this one is, say, yeah, you can just, so the one, so these are two separate, now we've colored them in one color here, okay, but that's just because we flattened them together, okay? We flattened the arrays to better plot the histogram. Actually, it's normally a three, one for R, one for G, one for B, okay? For each image, yeah, for each image, okay. All classes, okay. And all we're doing here is we flattened that into a single value. We've histogrammed that. So we're getting, so this one is one image, this one is one image. And we say that, okay, the amount of the intersection will help us decide its class. Right? So, and then after that, it's a k-nearest. So we're labeling our space. You can think of it as an embedding where we've labeled these points based on, so every one of these histograms is a separate class. And then we're just doing a class voting every time we get a new histogram. Like, where would this best fit? Right?
So you're going to distinguish the various classes of fish.
Yeah, exactly.
The fish are differently colored.
Yeah, or at least the images there are. I don't know how it would perform on the test set, so. Yeah. So in this case, it's more like the unique combination of colors of the background because it was there in a training set. Okay, I suspect a little bit more about this competition is that the second test set, the one which they don't give to you, that has different boats. Okay, and I suspect our method would be terrible there on the secret one. You know why? Because those backgrounds would have color histograms which are nowhere in our embedded space. They're not near any of ours. But the test set which is publicly available for the public leaderboard, that is on the same sort of data. That is with the same background. So we do fine. We do quite well, actually.
The second test set is available.
Yeah, I saw it there, but we haven't, it didn't download yet, actually. So. Yeah, it's a gigabyte in size. Okay.
Thank you very much.
Who's coming up next?
Yeah.
No, are we going to